Hi guys, in this video I'm going to give you a brief introduction about FIR, or also known as a finite impulse response. Okay, FIR filter is quite famous in digital signal processing as a digital filter. Okay, this is mainly because FIR can be implemented easily in hardware. FIR have a finite duration, it's quite stable comparing to IIR, infinite impulse response. FIR only have a zeros, it don't have any poles value in transfer function. Okay, because all of these reasons FIR are quite famous. All right, so as an engineer or physician or whatever that you are involved, so it's like a compulsory for you to know how does the FIR is working. Okay, how are we going to implement it? So whenever your supervisor or engineer or your lecturer asks you to design the FIR, okay, design for me a finite impulse response with the number of order of 4, or design for me FIR with the number of taps 128. So you must know which of the variable that you're going to change, how you control the variable, how you're going to generate the impulse response, how many times you must apply the delay. So every detail as an engineer you must know that. You cannot run from it. Okay, so let me start this introduction. It's quite easy actually. Okay, actually it's not that hard. We only have 1, 2, 3. We only have 3 different terms. And if you can see this particular portion here, the mathematical form, this is the summation, this is the multiply. So you're going to multiply and sum, you're going to multiply and sum and repeat again. How many times? Okay, it depends on the number of input actually. All right. So n here represent the number of order. So n equal to number of order. All right. So how are we going to determine the number of taps? So n plus 1 equal to number of taps. All right. So number of order here represent the delay block here. Let's say we have 1, 2, 3. So it's going to be 3. So if you have 1, 2, 3, 4, 4 number of impulse response or 4 number of weightage they're going to apply to the signal, it's going to be n plus 1, 4. As simple as that. All right. Okay. This mathematical form here, so we have one output, the impulse response, and also the delayed input. All right, so this is the block diagram representing the mathematical form here. So whenever you have an input, you're going to multiply with the impulse response, then you're going to add with the following input delayed, and we're going to multiply with the weightage. You're going to add, you're going to do it, repeat the process again until you get the output for n equal to 0. Then you're going to repeat again until all the input pass through this filter. This is the filter. The filter not going to move, only the input going to move from one delay to another delay until all of them flush out. All right, how many output that you're going to have is like the number of input. This is how many output, number of input, okay, plus number of taps minus 1. All right, let's say in this example here we're going to have 1, 2, 3 input. So 3 plus the number of impulse response here we have 4 minus 1. So the y going to have how many? We're going to have how many output? 4 plus 3, 7 minus 1, 6. So next you're going to see the y supposed to have like something like a whatever the value that we're going to calculate, 0, 1, 2, 3, 4, 5. Okay, we're going to have 6. 0 to 5 is a 6, right? Okay, so going to look like this, the output. All right, from this convolution process. All right, FIR is a convolution process in time domain and multiplication in frequency domain. You can do the FFT for this impulse response and multiply with the FFT of the incoming input signal. If you notice, this is the signal that we obtain from analog to digital converter. Whatever the analog signal here we have, okay, this is analog signal. Okay, we're going to convert to digital, okay, by using analog to digital converter. So how does this signal going to look like? So you're going to look like this. You're going to have in the form of impulse. Okay, So we're going to process this signal. That's all. Okay, this signal here representing this signal. After it's passed through the analog to digital converter, we're going to have the impulse response in this form here. Then we're going to do the convolution with the impulse response. Let's say for this example here, we have it like this, right? So you're going to multiply with this, do the convolution. All right, this is the xn, this is the hn. All right, as simple as that. Why we want to evolve in this process in the first place? Okay, in this case, we have a smooth sinusoidal signal. Okay, we have a smooth impulse response here. Let's say if you want to filter, why you want to filter? Nothing to filter there. So let's say another case here. I'll show you another case. What happened there? Why we want to use the filter actually? Let's say we have the sinusoidal signals like this, very influenced by the high noise component. All right, and let's say this is a sinusoidal signal that you have. When you convert to analog to digital converter, what you're going to have? You have an impulse response of the signal. Okay, we are going to have a high frequency component, a low frequency component. You're going to have every component there. Okay, so your the impulse response here is depend on the bandwidth or the sampling frequency of the analog to digital converter. Let's say 50 megahertz. So you're going to have a 50 mega sample, so for every second. All right, so what you're going to do when you change this input signal analog, okay, to digital. Okay, now what you're going to do, you want to process this signal. You don't want it to look like this. What do you want? You want this signal to look like this. Okay, so that's why you must apply a filter. Okay, this is our filter just now. Like just now we see, okay, the blue color here, this is our filter, impulse response. Okay, so you're going to multiply, you're going to do the convolution. So whatever this signal here, you're going to convolve with this signal. So you're going to get a smooth impulse, okay, which represent the pure sinusoidal signal here. Okay, I think you already get the idea. Okay, the overall why we are doing all this thing. Okay, all right, let me have a look. How does this thing actually work? All right, okay, now we already know our input here. Let me assume this is our input. We have 1, 2, 3, and we have the impulse response 1, 2, 3, 4. All right, okay, we have 3 input. Notice that 1, 2, 3. We have 1, 2, 1. All right, then we have the impulse response here. Let me substitute the impulse response value to the block diagram. We have 1, 2, 2, 1. All right, so 0 is supposed to be 1. This one, 2, this one, 2. So this one. Okay, instead of just multiply with H0, now you're going to multiply with 1. So now X in sequence, what are we going to have? You're going to have, let me see the value here. What's the value? This is just an example. For you to understand this complicated here, I'm just simplified to make it this a convolution process. This is our input, the simple input. It's like just a small portion from here. I'm just showing here this small portion here. What happened when we convolve with this impulse response? Okay, actually in real world, it's going to the whole bunch of this signal going to convolve with this impulse response. So it's going to take a long time. But in this example, I'm just going to show you this short example here. And what's going to happen there? We have just now what we have. Okay, let me have a look. 1, 2, 1. Right? Of course, the signal must have an amplitude, right? When you convert, its amplitude going to be normalized, right? That's the thing. We have 1, 2, 1. All right. So we have 1, 2, 1. The xn. All right. We see what happened now when y equal to 0. What happened there? So do we have any? Okay, the signal just came here. Whatever the signal, let's say the signal as I mentioned just now in the analog form. All right, and this will just arrive here. But in our case, it's not this signal, right? In our case, it's going to be this signal. This signal, all right, just arrive here. So what's going to happen? So the xn here going to represent this value 1. Okay, so xn, and this time 0. So x0 multiply with h0. You see h0 here, xn here, x0 here, multiply with h0 here. Then what is going to happen? Do we have any value here? No, 0. Do we have any value here? No, not yet. Not yet. Same. Right? So now what we're going to do here? Complete the whole process here. Of course, we have to complete the mathematical equation. So 0 multiplied h1 plus. Notice the sign there. Plus 0 times h1. Continue this side. Plus 0 multiply. Okay, come on, Sonny. 0 multiply h2 plus 0 multiply with h3. As you can notice here. Alright, now it's going to happen. This one going to be 0, this one going to be 0, this one going to be 0. So it's going to only to left with x0 multiply with h0. This one equal to what? We have the value here 1 multiply with 1 equal to 1. We already get the value for y0. So y0, we put here the y value. Alright, so now we have y0. Let me start from here. Okay, it's other way around. Okay, it's like this. It's better to look. Alright, nice. This is 0, y0. Okay, we have the value of 1. Okay, now we're going to repeat the process. Okay, let me just wipe this area because I don't have any space. Sorry about that. This is small screen. I don't have money to buy big screen. Alright, let me rub. Alright, let's go. Okay, now what's going to happen? So y, instead of 1, we're going to change into 1. Instead of 0, going to be 1. Sorry about that. Okay, now what's going to happen? This value here going to become here. Is going to migrate from here to here. It's going to be delayed by 1. Okay, going to from here is going to come here. So instead of 0 here, what we're going to do? We're going to substitute with 1. Now what going to happen here? The new value here going to come here. So now we're going to have here 2. Here is still represented by xn. Here we have xn minus 1. Okay, see, whatever the xn here is now going to have x minus 1. The same value, just now we have here 1, right? So now n minus 1, 1 minus 1, x0. Okay, it makes sense. Okay, now we try to do for y equal to 1. What happened there? Okay, repeat again from starting process. Now we have 2. 2, the new value here take place, as I mentioned. Now we have, let me write in the general form first. Yn, now y1, x1 multiply with h0. Okay, alright. Plus. Now what happened here? We have x1 minus 1, 0. Multiply with h1 plus what happened here? Here we're going to have 0, here we're going to have 0. So just write 0 multiply with h2 plus 0 multiply with h3. Alright, 0, 0 cancel out. So I can rub them off. I can just erase them off. Okay, create a space. Okay, that's all. This 0 just disappear. So what's the value for x1 now here? Now we have 2 times 1. Here what we have 1 now plus 1 multiplied by 2. Here have 2 multiplied with 1. Now we have 1 multiplied by 2. So altogether we have 4. Voila. So substitute 4 here. So let me make it 1 look smaller. Alright. This is 1. So 4 going to be higher. 4. Now this is y equal to 1. Now let me put it in better form there. 1. Okay, now we have to do what is the value for y equal to 2. We're going to do it the same process over 3, 4, 5. 3, 4, 5. Okay, as this equation I mentioned just now, how many output that we're going to have. Alright, so repeat the process again. So y equal to 2. What's going to happen? The same thing you're going to repeat again, until you got all the value here. We're going to substitute all the value here. This is our filtered signal. If you see this example here, for now we're going to have a filtered signal when you apply the convolution process. Thank you so much for watching my video. In the coming video, I'm going to show you the example in the MATLAB coding. Thank you. Bye-bye. Have a nice day.